Today's podcast, I'd like to talk about complex numbers. These are often very useful when we talk about circuits, especially oscillating circuits or when we have AC signals. So let me just review a little bit about what are complex numbers. So let's define the complex numbers, right? We remember from algebra, I is equal to the square root of -1. This is the piece that represents the imaginary part of a number. Now, right off the bat, this presents problems because I in circuits represents the current. So we're going to, rest of this class, we're just going to use I is going to be J, right? So that we don't confuse it with the current. So in your previous life, when you used I as the imaginary part, that was fine. In this class, we're going to use J. So if we have some imaginary number z, which is equal to a plus bj, right? That means a is the real part, b is the imaginary part. We can plot that on the real imaginary plane. And so a in the real, b in the imaginary, that represents z. And we can represent it by a and b, or we can represent it by the magnitude of z and some phase angle phi. And once we draw this picture, we can describe a few pieces, right? We can say, hey, the magnitude of z is just going to be the real part squared plus the imaginary part squared, square root, right? That's just Pythagorean's theorem. We can find the phase angle. Tangent of the phase angle equals b over a. We can notice that the real part of z, which in this case is a, is just the magnitude of z times phi. The imaginary part is just the magnitude of z times the sine of phi. And so the point here is once we know a or b, or once we know z in magnitude, we can switch back and forth, right? There's only so much information. And this whole mathematics of this should remind you a lot of vector notation, right? This was exactly the same math that we used in vector notation. And so let's imagine this imaginary number. It has a real part and an imaginary part. Let's use our definitions based on what's the magnitude of z times the cosine or sine of the angle. We can make those substitutions here. And then if we pull out the magnitude of z, we're left with the cosine of phi plus j sine of phi. But it turns out this can be written in another way as just ej phi. That's what we mean. They're equivalent. ej phi is cosine of phi plus j sine phi. But this is a much more compact notation and makes life a lot easier in the long run when we're talking about circuits, especially oscillating circuits. Okay, so there's one other thing we need to talk about before we sort of move on to the big idea, and that is the complex conjugate. Essentially, this is wherever there's a j, you make it a minus j. That's how you make a number a complex conjugate. So if you have z is a plus jb, the complex conjugate of z is just a minus jb. And if you multiply the complex conjugate, z star times the z, you don't have an imaginary part, right? It's all real. A squared plus b squared in this case, or the real part squared plus the imaginary part squared. But that is just the magnitude squared. So it turns out if you want to find the magnitude of an imaginary number z, you just take the complex conjugate, multiply it by the complex number, and you can find the magnitude squared. Okay, so now let's see how this can be useful in describing oscillating functions. So we've said we can describe this imaginary number as a phase angle and a magnitude, but we can also imagine that phase angle varies with time, right, in the following way. The phase angle is some function of time times omega t plus phi naught. So omega is the angular frequency. It's telling you how fast does the phase angle change with respect to time, and phi naught is just telling you about the initial conditions. Where is the imaginary number at time t equals 0? And so the upshot here is at time t equals 0, we could have some phase angle, some magnitude. At some later time, the angle is going to change. The magnitude is not going to change. We have the same magnitude, but the phase angle has increased. And then at a later time, same magnitude, phase angle has increased. And so you can see that as a function of time, this is just going to represent that vector or that arrow rotating around the real imaginary plane. And so we can use these imaginary numbers to represent oscillating equations. So let's look at an example. So here's our imaginary number. We're going to write it in polar form, or we can write it in polar form, the magnitude of z times e to the j phi, or we can write it in the a plus jb form. But let's imagine, for the sake of this example, that omega is pi over 2. So that means it's going to change pi over 2 radians per second. And that the magnitude of z is 2. So the length of our imaginary number is 2 in whatever units. It could be ohms, it could be volts, it could be amps. And phi naught is equal to pi over 4. It's telling us something about where z at time t equals 0. So let's look at our number. So we can say z, we can write it in this form, plugging in what we know about our particular example. The magnitude is 2, omega is pi over 2, phi naught is pi over 4. So z can be represented by this number, and we can see that it depends on time. And if we want, we can write down the real and imaginary part. But this is our imaginary number, depends on time. So let's see what that looks like. So let's look at 4 different times, 0, 1, 2, and 3 seconds. I can calculate the phase angle at each of those times. At time t equals 0, the phase angle is pi over 4. They change by pi over 2 each second. So then 3 pi over 4, 5 pi over 4, 7 pi over 4. Okay, so these are our times that we're interested in. Well, let's write z down for time t equals 0. Well, in the polar form, it's just this. If we break that out, we can use our trigonometry and we can write it in this form, and we can draw the picture which says, hey, our initial phase angle is pi over 4, length is 2, that's my imaginary number. And I can do that for each of the phase angles, or each of the times. And what you see is this vector is rotating with some frequency omega. Okay, and so that is what's going to be useful when we start to talk about a signal generator that oscillates with some frequency and starts with some initial conditions. And so the skill that you want to really develop is to go between these three modes, right? Because someone may tell you, oh, the initial conditions are that 0 at time t equals 0, but it's increasing. What's that mean? What angle? What phase angle is that? And write that down. And so that's, in class, what we're going to practice.